In the previous two episodes, we looked at using Docker and GitHub Actions to automate various testing procedures. This time, we're going to dive into creating unit tests and then using those various automation tools to construct a simple continuous integration pipeline that you can start using in your own projects. Let's go! In a somewhat contrived example, here is what the basic software stack might look like for an embedded project. We would have our main application that depends on some components or modules. These components would depend on drivers that talk to the hardware on our system. When it comes to continuous integration for embedded systems, it can be difficult or sometimes impossible to test these drivers, as you either need the physical hardware or a virtualized version of it. However, if you modularize most components of the system, you should be able to write individual tests for them that are purely software. For example, these components might do things like manipulate images, perform digital signal processing, or compute some other complex math. When you write unit tests, you will create main entry points for each component and ideally fully test that component along with any foreseeable edge cases. Sometimes, however, you need to mimic the behavior of your hardware drivers so that your components can run. In that case, you might create what's known as test doubles for your drivers or other dependencies that won't run in a virtualized or actual hardware environment. You'll often see people talk about stubs, mocks, and fakes. These definitions vary some, but often a stub means that you just create an interface for the double and have a simple dummy return value. A mock is similar, but it usually refers to something with predefined behavior that reacts to particular inputs. Finally, a fake is something with limited functionality and somewhat mimics how the driver or dependency works without needing the full hardware. There is growing interest in the embedded world to create hardware-in-the-loop continuous integration and testing. Here's a good blog post by Goliath. In it, Nick talks about using a Raspberry Pi that talks to GitHub Actions. Upon request, an automated script compiles and runs code on your physical device, like an ESP32. Test results and logs are then sent back to GitHub to show up in your project repository. We won't get into hardware in the loop for now, so let's go back to creating simple unit tests for our software components. Writing a main entry point for each test is possible, and it's often the way to go for smaller projects. However, it can quickly become cumbersome when you start having components that depend on each other, and as a result of this, it's usually helpful if we just turn to a framework that already exists for us. You can likely find a test framework for nearly every popular programming language. Since we've been working in C and C++ for embedded systems in this series, I'm going to use CppUTest. There are other C and C++ test frameworks like CppUnit, Unity, and Google Test, but this one is open source, seems to be well designed and documented, and it's also quite popular. So let's take a look at how to use it. The first thing we want to do is head to github.com and we're going to make a repository, much like we did in the previous episode. So go to New Repository, and I'm going to name this one C-unit-test. And then let's create that repository. You should get some instructions about how to clone that repository, so I'm going to open up Git Bash here. And I'm going to head to wherever I keep my GitHub repositories. Then I'm going to call git clone and the location of that repository that we just created. We cloned an empty repository, which is fine. So I'm going to go into that and we will minimize this window because we will come back to that in a bit. The next thing we're going to do is create a directory structure for our project. Now, I'm basing this on the Pitchfork layout, which is a fairly popular recommendation for a lot of C and C++ directory structures. It's definitely not any sort of standard, but I find it to be a good place to start. So feel free to go to github.com vector-of bool/pitchfork and take a look at the recommended layout here. And we're going to be mostly following this. So I'm going to go to my GitHub repository, so I'm in CUnit-test, and I'm going to create a few directories. src for source is where I'm going to keep all of my source files and header files for this project. I don't have any public-facing header files, so I'm just keeping all of the main code as well as the components, which is our modules or units that we're going to be testing. Next, I'm going to create tests, and this is where we're going to write the code and make files for our unit tests. And then I'm going to make something called tools. Now, this is where we're going to keep our testing framework, but I recommend not necessarily checking it into your repo as it will take up space and the testing framework's publicly available. But you can if you'd like to, if you want to make the full thing completely modular. The first code we're going to write is going to be a very simple project. I'm going to create my component here that I'm going to call average. And this can be thought of as a module or a submodule, but I'll call them components as that's what our testing framework looks like. In average, we're going to write average.h, which is our header file. Let's open this up. We'll write our header guards, which is generally good practice as it prevents multiple declarations of the functions in this file. Then we're going to create our only function for this particular component. In this case, we will pass in an array and along with the size of that array because we're working in C. And this will just compute the average of all the floating point elements in that array and return that value as a floating point. Then we will close out our header guards and call this good. So let's save this and let's create our C file for the actual implementation. All this average function will do is just go through each element in that array. The size of the array must be passed into this function. It will add them all up and then it will divide by the size, giving us a basic average or mean. Let's save this file. Now we're going to write our main.c in order to test this. However, you have to imagine that main.c is going to be the actual application. This is the application that users will compile, or perhaps you will compile as part of a continuous deployment functionality that users will then just download the executable for their machine. This is for the end user. This is not necessarily any sort of unit test. But for the sake of just demonstrating what an application might look like, let's go ahead and write a very simple test for this. All we're going to do is include our standard input output. We'll include the average header file, which we will make sure in the Makefile is linked appropriately and that header file can be found. We're going to set a very simple array where when it's averaged, it should come out to be 1. And then we're going to call our average function, pass in the size of that array, and then print out that result. This should be pretty straightforward. Next, we're going to write our Makefile so that we can actually build all of this. And this Makefile is going to be a useful template for us, or a useful tool for us that we can call in order to either build the application or build our tests and run those tests. And we will rely on this Makefile when we go to create our Docker image and ultimately GitHub Actions workflow. Note that you can use CMake or AutoMake or any of the other tools out there. I'm just using Makefile because it comes with a lot of Linux distributions and it's kind of a bare bones way to get started. But I do find that Makefiles are a little tricky to scale up to larger projects sometimes. I like to create the tool definitions or defaults for these tool definitions for GCC and G++ if they are not already defined in your environment. So I always like to put these up front, and this question mark equals says set the variable CC to GCC if it's not already defined. It's kind of like setting a default. Next, we'll create some settings. So the location of all the source code we will set as source directory. We will also want to tell this Makefile where the tests are located once we go and write those unit tests. I like to specify a build directory. Normally you might actually have a build directory where you put the application itself once everything is built, or you put the object files as they're being built. I'm going to be lazy and just drop the application right in this top level directory anyway, and then we'll name the application itself. This is going to be targeted for Linux systems or Unix and Linux systems, so this should work on Mac OS. And most of those come out as ELF files when you call GCC or G++. So we're going to name the output as app.elf. Next, we want to include the header files for our different components that will get compiled into object files and then ultimately linked to that main or app.elf that we're going to be creating. I generally like to put these in C flags, so just create a running list. That's what the plus equals does. It's just appending, and it's going to append this string -i for this include, and then the location of that average component. In this case, it's in src/average. Then we need to tell the Makefile where to find our main application or the main code, and that's going to be in main.c. That's in the source directory. We'll add that to the C sources list of source files. Make has some powerful ways to automatically find files, but it can be a little tricky to work with. You have to know some of the functions and commands. In this case, we'll be using the wildcard command that automatically expands out to a list of files and directories given by the pattern here. In this case, we're saying look in the source directory /average and find anything that ends in .c and then create that as a list that gets appended to the C sources variable. Just to demonstrate, we can also add some compiler flags here. So I will add the all warning or wall flag to my C flags. Even though I don't have any linker flags for this simple demonstration, I will show you here that yes, you can create your own list of flags that we will add to the actual build command or the GCC command. But this is a good template that I like to follow, so I usually just include it anyway in case I later have linker flags. Here I'm going to be using some implicit rules that can be a little tricky to work with sometimes. I'll be using the pattern string substitute, or pat_subst, to generate a list of .o files or .object files based on the .c files found in the C sources variable. So this is how we generate our list of object files that will ultimately become targets for us in just a moment. The phony keyword avoids any target name conflicts that might be with a file name. If that file name is present in the project, it's generally a good idea just to include these in your Makefile. And so the all rule is what happens when you just type make. That's the default rule. And in this case, the default rule says go ahead and make whatever's in the name variable, and that's going to be our application, or app.elf. For building the individual modules or components, I will call them components, we want to create a target for each object found in the CObjects variable. What I'm writing here is a static pattern rule. The idea is to create a target for each item found in the CObjects variable. In this case, the target is given by the stem, which is that %, and then the target is .o. So on this second line, where I have stem.o :stem.c, this is saying the target found by this stem.o, which is given by this expansion of C objects into stem.o and stem.c, and the prerequisite for each of these targets is the stem.c files found. In this case, for example, we would probably have average.c. Due to this pattern substitute command, we now have a list of .c files given by C sources. So average.c becomes average.o in these C objects. And any of those components you have would be found by this, and you would have to list them up here in C sources. So then if you have, say, sum.c, you would also have average.c, sum.c. Those would become average.o and sum.o in this C objects variable. And then those get broken out. So now we have average.o as a target, and the prerequisite for that is there must exist an average.c, which there does. And then similarly, it would also run this for, say, sum.o, which needs sum.c in order to compile. For each of those, we run our compiler, in this case GCC. We set any compiler flags that were given above. In this case, we're going to enable all of the warnings. -c says to build the file without linking. So we don't need to link any of these necessarily. They should be able to be built independently, which is perfect for our unit tests later. The $@ symbol is the name of the first prerequisite. So in our case, it will be average.c that's being built. -o is our output file name. And that file name is coming from this $&, which is the file name of the target of the rule. In this case, it's referring to this stem.o, and the only module that we're going to be building is average, so it's average.o. Notice that I'm not putting any of these in a build directory. They're just going to reside next to wherever it finds the .c, which is one way to do this. You might also see people building it in a, say, build folder, which is fine. That's just different ways to construct your Makefile. Then we need to build our application. In this case, our application is given by name, so app.elf, and it's going to depend on all of the object files that we listed in C objects. We'll call GCC along with those object files. We're going to output our app.elf file, and we're going to put it in our build directory. Remember that build is just the current directory. So if you're going to be putting it in a build directory, you may want to check first to see if the build directory exists, and if not, create it, but I will skip that for now for simplicity. And then of course add any linker flags, which we don't have any. Then we're going to remove any compiled object files. So if you call make clean, this is the clean target. All it's going to do is just remove all of the files that are listed in the C object. So any of our .o files. It will not remove our app.elf. Feel free to remove that if you'd like here. But this is a way to clean up the build process and you're just left with the built file. Go ahead and save this. Note that we made this Makefile, and the testing framework we're going to be using is really intended for Linux. It should run on Mac OS, which is BSD based, but it is going to fail pretty hard on Windows, which is fine. Luckily, Windows gives us WSL, which is Windows Subsystem for Linux. If you do not already have WSL installed, I recommend checking out the installation process for installing WSL. All you need to do is open up a command prompt in administrator mode and then just type this command and Windows will install it for you. I recommend the Ubuntu distribution because we're going to be using the Aptitude Package Manager to install packages that are necessary for us. So go ahead and install this if you don't already. And I'm going to open up a command prompt where once here and WSL is installed, I just need to type WSL in order to get into my Ubuntu distribution that resides in Windows. Once here, navigate into wherever this repository is. Feel free to take a look in there. There's our Makefile. And if we wrote it correctly, all we need to do is type missing separator. Well, we have an issue on line 34. So let's see what I messed up. All right, so this is likely one of two things. Either these are supposed to be tabs instead of spaces, or I'm having different line endings because Windows. That shouldn't matter too much. So if you're using Notepad++, you can go to Edit EOL Conversion and use carriage return line feed or any of these, and it will convert all of them. Interestingly enough, Notepad++ should be smart enough to know that this is a Makefile and know which types of spaces and tabs to use, but it does look like it puts spaces in here. The other thing we can do is if you go to Edit, you can go to Blank Operations, Space to Tab Leading. That should convert all of my actual spaces here into tabs. Okay, let's try this. Make, there we go. So it was definitely spaces and tabs issue. So now that make works, we have our app.elf file, which you can see appearing here. Also, if you're curious, you can see the object file showing up in our source directory. So we just need to run app.elf. Sure enough, we get average of 1.000 as our output. Writing simple unit tests can be easy, but you will likely be quickly overwhelmed. So we're going to rely on a popular existing framework for C and C++ code known as CppUTest. And this is going to help us perform our unit tests. It was written for Linux and Unix, hence why we're using WSL, and it should work on Mac OS. So if you're on Windows, yeah, you're going to need to install WSL like we did, or use something else like Cygwin. To start, we're going to want to download the latest release, or the latest stable release from CppUTest. Now, they list 3.8 on the site, but I find if you go to their GitHub page, and you head down to releases, you will see that there is a nice, brand new, shiny CppUTest version 4.0 that is probably about 2 or 3 years old at this point. We are going to download this. So go to Assets. We're going to download, at least for Windows, I'm going to download the zip file because it's a little easier to work with. So I want to head to my Downloads folder, and I'm going to unzip this. So extract all, and let that finish extracting. So we're going to go into here. This is CppUTest. Sort by name here. Feel free to look inside of here. It's all open source, which is nice. And I'm going to copy this. And I'm going to go back into wherever I keep my project that we've been working on. So C unit test. I'm going to drop this into tools. The intention was that CppUTest was not really supposed to be included in your project. Included or not, if you'd like, I'm going to show you a way to modularize that by using a Docker file rather than having to transport this with your repo if somebody were to say clone it or download all of your source code. We will need to build CppUTest from scratch. So in here, head to Tools. You should see CppUTest. I'm going to go into there. And this is the top level directory of that tool. You will need to install some packages. In this case, you will want Build Essential, AutoConf, AutoMake, and libtool. Build Essential has GCC, G++, Make, all of our linker tools that are useful for building C and C++ projects. And AutoConf, AutoMake, and libtool are useful ways for automatically generating things like make files within larger projects. CppUTest needs those tools in order to build itself. Note that you can also install all of these on Mac OS by using Homebrew. So while you don't have Build Essential, you do have things like GCC, which should come with G++, as well as Make, and then the other three tools, AutoConf, AutoMake, and libtool. Now that we're in the top level directory of CppUTest, we're going to call autoreconf-I, which will set up some configuration. And from there, we're going to call this configure script, which will check to make sure that everything's installed that we need to build the project. And finally, we will call make to actually build CppUTest. Note that this is a bit of a process. The idea is you should only have to do this once. You can also find CppUTest as a package that you can just install globally on your system, and then you could just link to that. But I'm showing you how to do it in a modular fashion in case either you want somebody to be able to download CppUTest with your repo, or as what we're about to do is create a Docker file that performs these steps automatically so that you can create a modular testing system that can be executed, say, as part of a GitHub Actions workflow. We're going to get out of that, and we're going to be back in the top level directory. Now I'm going to go back to the GUI so that you can see what's going on here. In this, we're going to create a new Makefile, but we're going to do so in tests. What we want to do with this Makefile is to have it automatically find the individual unit tests that we're going to create that test the different components of our system. We're going to be using that wildcard command again to expand out all of the subdirectories that are found within this tests directory, and then those become our test directories and ultimately our targets. Here's where we say if we just call make as the default rule, it's actually going to go ahead and run make on all of the targets that are defined by test dirs, and that's just a list of the subdirectories found within the tests directory. So for each subdirectory found, which is our new target, it's going to call make-c, which says run C from the context within a particular directory, and we're going to give it that directory. Remember that the variable @ refers to the target file or target name given in the targets list here. So in this case, whatever that target directory is, we're only going to make one, which is average. Go ahead and call make-c, which says run make from within the context given by the average subdirectory here. It's essentially the same as going into that directory and then just calling make. And then finally, we're going to have the clean version where we can have each of the tests clean themselves up. So for each directory within the test directories, go ahead and call make from the context of that particular directory, and of course, make clean. The idea here is that we will create a Makefile for each unit test, and then this global tests Makefile can be called in order to run all of those tests, or in this case, clean them all up as well. Go ahead and save that, and let's make sure that we have, these are spaces, not targets, so we will go to Edit, Blank Operation, Space to Tab Leading, and save this again. So now these should be tabs to hopefully avoid that error from last time. So now that we are in the top level of tests, we're going to create unit tests for each of our components. So we want to create a unit test for average. We're going to go in here and create main.cpp. Note that CppUTest is written in C++, so it's generally a good idea to write your tests in C++. However, there is a way to make it test C code, so it should work with both C and C++ target files, or whatever the individual components are written in. But you are limited to C and C++ for this particular framework. This is a bit of a template that comes right out of the CppUTest documentation, where the main entry point for each test is essentially this file. You can modify this as necessary, but this is a really good place to start, where we're going to call this run all tests functions that's found in the command line test runner namespace. And don't forget to include that file, that header file that you can find within CppUTest, and we will make sure that our Makefile knows where to find this within that tool. So let's save this. And then we're going to write our actual unit test, which is test.cpp. The idea is you can copy each of these subdirectories to create a template for your next unit test. So main.cpp would remain the same, and then you would just write new unit tests within this test source code. So the first thing we want to do in our unit test source code is we want to include the test harness header file from CppUTest. We also want to include our particular component header file. Note that because it's written in C, we want to wrap that with extern C. If this was written in C++, you would just include it directly, just like that. But because we are in C, we're going to leave that there. Note that all tests must be part of a test group. So we're going to declare a test group using the test group macro that's found within CppUTest, and we're going to give it a name. In this case, we're going to call it average test group. And this is just a name you can come up with. Just make sure when you create tests, you always refer to this group because those tests need to be in a particular group. There are two functions that are defined, setup and teardown. If you need to do any sort of setup code, say allocating memory or so forth, you can do that in this setup function. And the CppUTest knows to look for this function. It will call this function before calling any of your tests, and then it will call teardown after it is done with any of the tests. And this is if you need to deallocate memory and so forth. I will leave them blank for now, but leave this template here, just so you remember that you do have the option to do any sort of setup and teardown prior to running your tests. Next, we will define our first actual unit test. The two parameters to this test macro expect the name of the group. In this case, we are assigning it to the average test group, which we defined up top, and then the name of the actual test. In this case, we're calling it simple test. Just like we saw in our user application, we are going to create an array, in this case, a static array, and then we are going to use our average function to compute the average with that static array. And we know that this should come out to equal 1. And we're going to use the macro in CppUTest known as check equal to check the value of this output to a known good value. You could compute this value somewhere, but it's generally a good idea in unit testing to have a known good value that you test against. That should be a constant value that you compare your results to. And this will either pass or fail the test, and you will see the outputs of that in a moment. It's generally a good idea to test your edge cases. So if somebody were to come along and modify or refactor this average function, you will want to test any edge cases that should be caught. In this case, what happens if somebody supplies an array of length 0? Now, C++ does not let you declare arrays of length 0. That's actually a good thing in the compiler that it catches. But in C, a lot of times you can. You can get away with just passing a pointer that points to nothing, and you say, hey, compute the average on that pointer to nothing, and you will probably get something that's like null or some garbage value. In the case of C++, you're going to get not a number. So this is not a good thing. We don't actually want any of that to return because that might mess up code if somebody were to use the average function in their bigger application. We want, as part of, say, our specification for average, we want it to return 0. If you give it an array of length 0, we say that we want this to return 0. So we're going to check that average value to 0. Now, our function does not actually do that at the moment. This test should fail, which is perfectly acceptable. So let's save this. If you are curious about where I'm getting this information from, if you head back to the CppUTest main page, which is CppUTest.GitHub.io, you can go to the core manual. I definitely recommend reading through some of this getting started, which is exactly like what we're covering in this video. But you will want to go to the test macros, and you will see all of these macros that I'm using. So test, ignore test, test group, check, check text, check false. Lots of conditions you can do. There's string compare, close enoughs, things like that, bytes equals. So take a look at these possible assertions. We're just using check equal for our basic tests here. So make sure you've saved your work, and we are going to create one more Makefile that exists as part of our unit test to specifically test just this average component. So I'm going to create a Makefile in here. I'm going to go ahead and open that with Notepad++. This Makefile is going to set a number of variables, and then we're going to call a Makefile that's already in CppUTest in order to run the tests, in order to build and run the tests. The first thing is we're going to need to name the component, and this is required by the Makefile worker, which I'll show you in a moment. We're going to call this component average. We're going to use this name throughout setting our variables in order to say, hey, where is this directory? So it's a good idea to name your component name after the directory that this unit test is sitting in. I want to thank Mateus Mbar for posting this really cool template for dynamically generating absolute paths relative to this particular Makefile. We can use that in order to set a lot of our variables, because I find that when you call CppUTest, it generally wants things in absolute directory paths. And so we can dynamically generate that using a number of commands, in this case, the directory, real path, and first word commands that will generate that absolute path to this particular Makefile. And then from there, we can say, hey, what is the path to our whole project? And then define where the source and tests directory are. Let's go to our tools. Let's go into CppUTest. If you go to build, you should see this makefileworker.mk. We want to call this Makefile, but in order to do so, we have to set a number of the variables that are required. So in this case, include directory, source files, test source directories, and so forth as outlined here. There's some optional ones, like the component name is optional, but it does generally help. So once we've defined these, we can call this Makefile and it will run the tests for us based on the source directories and files that were given as part of these input variables. So we can close this. CppUTest home is one of those variables that should be declared. I believe it is a requirement. And we are going to set it if it's not already set by something else. So if you install CppUTest somewhere else on your system, you can set that variable elsewhere, say outside of a Makefile, and this default won't be picked up and it won't overwrite your definition of this variable. But if you don't define it, it will by default look for CppUTest in the directory CppUTest in the tools directory that's in our project. And this is why I recommend naming the components and the unit tests the same name. So our component name is average. That should be found in a directory in the source directory, as well as a subdirectory with that same name in our tests directory. So as long as all those names match up, this should work. Otherwise, you will have to set these to something else. So if you name it average_test, you will have to name our test source directories that as opposed to just average, which I will show you in just a second here. Sometimes CppUTest does not get linked correctly, or sometimes it struggles to find the header files. So it's usually recommended that as part of your include directories, you go ahead and append the include directory found in the CppUTest. So in that home directory in CppUTest under tools, it will look for that include directory for the header files so that you can actually compile your unit tests. So for example, these header files may not be found if you don't do this. Sometimes they break. So it's usually just a good idea to go ahead and include that. Then we want to set the location of the source directories for the unit tests. In this case, it's in tests, and it's the component name, so tests/average. If you copy this template to another unit test, ideally all you should have to do is just update this particular name. And if you were really slick, you could find the directory that it's in and use that as the component name, but I will leave that as an exercise for you to figure out. At this point, we should have all of these required inputs defined. So include directories, source dirs, source files, test source directories, test source files. We are not using mocks since that's outside of the scope of this video, but you should have that defined if you were using the mock framework. So we have all of those variables defined, and all we have to do is say include and the location of that Makefile worker. So let's save this. And if we did this right, we should be able to go into tests. We should be able to go into average, which is our individual unit test, and we can call make, and that will build. And I forgot something in test.cpp. Looks like I forgot a semicolon. Ah, right. When defining a test group, you absolutely need a semicolon after this macro. I did not look into it, so I can't tell you exactly why, but for individual tests, you do not need semicolons. So just keep that in mind. So let's save that and try this again. So if we call make, sure enough, this does work, even though you see an error here. Take a look at this where it says 2 tests were run, 2 checks were performed. We didn't ignore anything or filter anything out, and there was 1 failure. And because of that failure, make actually fails with an error code of 1, which is going to be useful in a moment when we automate this whole thing. Now, if we go up 1, we have that overall Makefile. So from here, if we call make, it should go through all of the directories found in the tests directory and call those individual make files. So just by calling make in this directory, we run all of our unit tests. I hope you can see how we're starting to build out this automated framework, even though it involves a number of make files in order to do so. Ideally, when you go to create new components, you can easily create new unit tests. So from here, let's go into our top level Makefile. We're going to create a target that says run all of our unit tests. To do that, we're going to create a target known as test. So if you call make test, this will run, and it's going to call make from within the context of our test directory. So it's the same thing as going into tests and just calling make from there, just like we saw a second ago. And it's usually a good idea to offer a way to clean out any of the built object files. So test_clean will just call make clean from within that tests directory. Go ahead and save this. And let's go back to our command line. So we're in tests right now. Let's go up to our top level directory. And remember, we can still make this. Oops. Guess what I forgot to do? So we're going to go to convert space to tab leading. We're going to save this. And this should have it already. So yeah, we're good. Let's try this again. So this should still build our app.elf file just like before. We can call make clean. That should clean out all the object files, but still leave that app.elf. We can also call make test. That will run all of the tests because it will call that Makefile at the top level of the tests directory. Sure enough, you see the test report. So 1 error was found, and make throws errors all the way back up to this particular Makefile, which is fine. That's actually what we want. And of course, we can call make test_clean. That removes all of the object files from the testing framework that CppUTest generated. I realize that this is a lot to get through just to get a basic template for demonstrating how unit tests are constructed. But keep in mind that we needed to write a main in order to simulate what an actual application would look like. We wrote our components in average.c and average.h. And so if you have a team member or somebody wanted to do a pull request, they could just create another component as part of this and then update your application file. And then because this is intended for medium to larger projects, you would then want to go into tests and create a unit test to test that particular component. And it took us a while to set up all of the make files to do that, but the idea is that you would just copy, say, this average component, use that as a template for the next one, which comes with a make file that you don't have to update much. The other make files should already be set as part of your template. You shouldn't need to change those because they go ahead and build all of the different components and all of the different tests if you say call the target make test. As I mentioned, this is a template for larger projects in order to have multiple contributors to it. Hopefully by breaking things into components and unit tests, it's easier to set up continuous integration and continuous testing so that other things don't break down the road and things are modularized in such a way that individual contributors know what they need to do and know that their parts will work with the whole project. The next thing we want to do is modularize the testing framework by using Docker instead of CppUTest. To accomplish that, I'm actually going to go ahead and delete CppUTest from my tools. So yes, I want to get rid of CppUTest. It is gone. I'm also going to create a very quick .gitignore so that some things don't get checked in. Anything that gets built as part of our project should not be checked into the repository, so any of our object files or the output application elf file. And just in case somebody follows these instructions and decides to install CppUTest in the tools directory, we are going to make sure that also does not get checked in. So we can close .gitignore for now, and then we're going to create a Docker file. I recommend watching the first episode in this series to learn how to work with Docker if you have not done so already. We're going to start with an Ubuntu image for our Docker image, for our custom Docker image. Then we're going to install some build tools. Just like we did to build CppUTest, we need to install build essential, autoconf, automake, and libtool in that image. Next, we're going to copy all of our source and unit tests into that Docker image, along with the Makefile, because we will need that. Then, just like we did in the command line, we are going to download and build CppUTest, and we're going to put that in tools. This is just an automated way of doing that, so people don't have to do this manually. They can just run this Docker image. So to get the location of this, I recommend going to View on GitHub. We are going to go to the releases, wherever that is. There it is, releases. Instead of .zip, we're going to get that tarball. So let's copy this link address. And we're going to use wget in order to download that. Hopefully that link does not change over time. Next, we will untar that file into a directory. That directory should be called CppUTest-4.0, and we're going to move and rename that to CppUTest. Remember, CppUTest is the name of the folder that is expected in our make files, so we should keep it to that unless you plan to change all of those make files. And just like we did on the command line, we're going to go into CppUTest, we're going to call autoreconf-i, then /configure, followed by make. Finally, we need to set the entry point for whenever we run this Docker image. All we're going to do is call make test-c to run from the context of the project directory. This is the same as calling make test like we did earlier. It should run all of the tests given by our Makefile. And so now you can run this locally, assuming you install CppUTest like I just showed you, or you can run this Docker image, and this will call that Makefile for us. Let's save this. Let's go back to our command line. We should have our Docker file in here, and we're going to call docker build. We're going to tag this image as unit tests image. Note that we can use the -f here to specify a particular Docker file somewhere, in this case just the Docker file. This is useful in case you want to have multiple Docker files within your repo to test different things, do different builds. So maybe this one is dockerfile.unit-tests, and so now you can supply it that Docker file. Otherwise, Docker will automatically look for something named Dockerfile with no extension in the directory you give it, and we need to give it the context of the current directory. So you could do this in a different directory, but we're going to do it in the current one with dot here. If you're doing this on your desktop, note that you need to have Docker desktop running. Looks like I've already created a unit test image earlier when I was testing this, so let's make sure we remove that before creating a new one. So with Docker desktop running, we're going to build our image, and that's going to take just a moment. With that image built, we want to call docker run. We want to automatically remove that image when we are done, and we're going to run the unit tests image. So that's going to fire up that Docker image, create a new container, run that container calling make test within that project directory that was created. As before, we should see one failure from our tests, and make should fail. Make should leave with an error. That's perfectly acceptable. But you definitely want to see this output, which is the output from CppUtests. From this, we know that CppUTest is working within a Docker image that is built automatically. It's downloaded and built automatically within that image. So now this whole framework is completely modular. So if somebody clones this, all they need to do is build that Docker file in order to run the tests. They don't need to put CppUTest in tools and go through that first part. Additionally, we can now create a GitHub Actions that will do this automatically in GitHub for us, so that if somebody who's part of your team pushes a new change or if somebody performs a pull request because they want to add changes, all of this will get done automatically for us on a server somewhere. And this is what makes continuous integration work, by having this automated testing process. If you watched the second episode, the one just before this, you will know that we can create our own GitHub action workflows. To do that, we need to create a .github directory. In there, we create another directory called workflows. And the naming of these directories is very important because this is what GitHub looks for in your repositories in order to automatically execute different workflows. We're going to create a YAML file. So GitHub Actions looks for these YAML files in the workflows, and we're going to call this one unit tests. Let's open that. We'll give it the name unit tests. And let's say that all of the unit tests will run every time there is a push to this repository. We're going to define just one job here. This is going to be Docker unit tests. And GitHub Actions gives us an Ubuntu virtual machine to work with, among some others, but Ubuntu is generally pretty easy to work with. We're then going to run our Docker image in that virtual machine. For this job, it's first going to check out this repo by using the checkout GitHub action, just like we saw in the second episode. And just like we did locally, we're going to call Docker build to build that image using the Docker file that we provide in this repository. And finally, we will run that image and use the RM flag to clean it up whenever we're done. Just remove that image. Just like we did locally, always a good idea to test locally and then script it to run automatically somewhere else. So let's save this. And I will bring back up git bash. So if you're on Linux, your command line system will work. I'm going to do all of this from git bash. So we can check out our status here. Since we added a lot of things, it's generally not a good idea to add a bunch of things and then check it in, but this is a demonstration. We will add all of those files. We will commit all of those files, give it some good message, and then we will push them to our repository. Hopefully that worked. Let's go back and take a look at unit test. So we will probably need to refresh this page. Let's go into actions. I'm going to remove this so it's not very distracting. Sure enough, an action is running, created unit test framework. Let's click on this to look at our actions. It's building the Docker image at the moment. Feel free to look through these steps to see what happened. This should be similar to what we saw when we did all of this locally. And it looks like run image failed. Well, let's go see why it failed. So drop it down. So the automated process didn't actually fail. What failed was our tests. So here we see the output of CppUTest. So if anybody checks something in, they can look at actions, they see something failed, they can look at the logs, and sure enough, this is because CppUTest ran successfully, and it failed one of our tests, which is great, which is exactly what we predicted. And because make throws errors, the Docker image throws errors. And because the Docker image throws errors, GitHub Actions receives those and shows that as one of the steps in the workflow as failing. This is perfect. This is exactly what we want. And if we go to CUnit-test, our little X shows up here showing that one of our tests failed. This is fantastic. This means that our unit tests are working exactly as desired. So let's go create a fix for our unit or our component. We're back in our directory here. Let's go to source. We're going to go to average, and we're going to go into our source code. Remember how I said this does not handle size 0 very well, or at all. To fix it, we're just going to add a very simple guard clause. All this is going to do is check if size is 0 and return 0. Now, for your actual code, you may not want to do this if you're averaging or summing arrays. You may want to return an error or something else, but let's say part of the specification for this particular component is to return 0. So now we are catching that edge case, and we are returning 0 as expected. It's usually a good idea to test this locally, so you might want to run that Docker image locally before you check it in. However, let's say we didn't. We're going to go back to our git bash here. Sure enough, we modified something. We're going to commit it, and we're going to push. Let's go back to our project. Let's go to actions. You can see the previous workflow that ran, and now we have the new commit where we fixed the average function for zero length arrays. We're going to go into this, and we're going to take a look at our workflow here and let that run. Once that's done, go ahead and take a look at the run image step, scroll down, take a look at the log, and here's the output of CppUTest where it says 2 tests were ran, and there were no failures, and then so make exited without any sort of error, which is why we get check marks for everything. And if we go back to the top level directory of our repo, sure enough, we get a nice little check mark here saying all of our tests have passed. I know this was a long one, but I hope it helps you get started creating unit tests and continuous integration pipelines in your own projects. Good luck and happy hacking!